Да, вроде. Поехали. Okay, so I will talk today, it's my title, metric invariance of spherical harmonics. It's really a toy talk. I will talk about very, very elementary stuff. I hope that it will be really understandable for students. But anyway, so what we will do, first of all, I will remind what means spherical harmonics. Possibly people who work with differential equations met them sometimes. So spherical harmonics is solutions of two equations. One equation, it's one equation is Euler equation. It simply says that we consider functions in variables. So x, y, z, it's the standard coordinates in R3. And the first equation says that we consider homogeneous functions of degree k. And because I said that I will consider only smooth solutions, it immediately means that they should be homogeneous polynomials of degree k. And the second.
K is the same?
Yeah, this k.
This k is the same as the k below?
Yeah. Yeah, k will be fixed for whole talk. It will be just degree of polynomials that we will consider. Да. Что?
О, это лучше.
Королев восхищения. Те билеты. Okay. Oh, yeah. Now it's much better. Okay. So spherical harmonics, they're just solutions of two, I would say, classical equation. One equation is equation for homogeneous functions of degree k, and the second equation is just Laplace equation. So if you will require that solution should be smooth, in other words, I will consider homogeneous polynomials in x, y, z of degree k, and they are harmonic. Okay, how to formulate this geometrically? So let's denote it by E with symbol I. It's these two equations and their prolongation to the level of I. So really we have this, the only statements they will write. So we have first equation, it should be equation of second order and derivatives of this equation. So it will give me, let's call this E2. There is also E1 here, but it's not important for us, so I will start with E2. So the second, it will be E3, and etc. What we can say about this, first of all, it will be not infinite sequence. It will be ended on the level of k, because it's a k jets of smooth solutions. So it means k jets of polynomials of degree k. So it means that on the level k plus 1, we will get 0 for this short sequence. No. And you can check, it's not really easy, but you can check that this all fibers of degree of dimension 2. So this is how this behave. So let's see what we can say about the situation. So we have a group of rotations in R3. It's our group SR3, this one. So this is symmetry group, the symmetries of this equation and this equation. So it's symmetry of this our system of equations. And also all these EIs, because they're given by very simple equations. So all of them are just affine algebraic manifolds in jet spaces. And so from algebraic point of view, you have this tower of affine manifolds, bundles of dimension 2, and we have action SO3 on this tower. And so we have really two problems here. We will consider two problems, algebraic and differential. For some reasons, namely because of the Lee-Trichet theorem, it's much easier to compute differential invariance than algebraic invariance. And I will do both. So I will discuss algebraic invariance and differential invariance in parallel. So this HK, it's say space of solutions of this equation, or it's simply a vector space of harmonic polynomials of degree k. Because solutions are just harmonic polynomials of degree k. It's SO3 module. It's finite dimensional space. We just will see dimension of this. And what is known about this space that in this space is realized all irreducible representations of SO3. So just simply list of irreducible representations of SO3. The second, so if you consider this vector space, and we have a linear action on this vector space, just change of coordinates in polynomials of degree k, and functions that invariant under this action, we'll call, so this is title, algebraic metric invariance of spherical harmonics. So, okay. And the field of, I will consider rational invariance, but because it's clear that rational functions that invariant under SO3, it will be simply ratio of two polynomials that also invariant under SO3. So we can talk about polynomial invariance or rational invariance, it doesn't matter. For some reasons, and mainly because of Lee-Trichet, we will use field of rational invariance. So notation, this is F, A, K. A is for algebraic, F for field, and K for degree of polynomials that we'll consider here. Now, together with algebraic invariance, we have, because we have this action SO3 on all these spaces, E2, E3, and so on, K. So this also define manifolds. They're not vector spaces, but define manifolds. So you consider rational functions on these manifolds, say on the level some I, and rational functions that invariant under this section we will call differential metric invariance of spherical harmonics and order I. Okay, and so the corresponding field, this one. By the way, what we can see that really any algebraic invariant is a differential invariant. Algebraic invariant means that it depends only on coefficients of our polynomial. And coefficients of our polynomial, they are derivatives of order k. So it means that you simply consider special invariants that have only expression in jets of or higher jets of order k. Okay, so now some very funny stuff. Really, spherical harmonics is just so well developed theory, and mainly it was developed by people who works with Hilbert spaces and topology and stuff like this. So there are a lot of constructions in spherical harmonics that use it integrals and stuff like this, some kind of functional analysis. But because I will work with mainly algebra or differential algebra, so I will try to avoid using possible integrals, and we'll try to substitute this integration by derivations. It's very funny, but it can be done. So the first observation is the following. Let's consider so-called while algebra, the notation for this A3 or AN if you consider n-dimensional case. So this is algebra of all linear differential operators on R3 that have polynomial coefficients.
Scalar.
Huh?
Scalar.
Yeah, scalar. Yes. No, everything will be scalar, right? So in this associative algebra, we have, first of all, two Lie algebras. The first is algebra SL2. It's algebra, very funny, but very important algebra for us. It will be generated by three operators. R is distance, so R squared divided by 2, and delta plus 3/2, and the capital delta divided by 2. So this is just diagonal operator. This is our Laplace operator, and this is just multiplication by R. You can check in this really fun observation that you really have enhanced algebra SL2. So if you take commutators, you will get exactly commutators in SL2, this so-called while basis. And there is another algebra that we maybe we should consider this algebra first. It's really Lie algebra of SL3 Lie group. So this algebra generated by three rotations. So this rotation in XY, this in XZ, and this is in YZ. So three notations. And this is also as Lie algebra inside of our R3 algebra, while algebra. So what's known about this situation? It's in general situation, it's called Hoare structure. So first of all, this is algebras mutually commute.
You say Hoare, Peter Hoare.
Yeah. So it's very easy to check it because all these operators that goes in SL2, they obviously commute with the rotations. So the second observation that if you take universal enveloping algebra of SL2, so just take this three operators that generate SL2 and take algebra that constructed on these three operators, you got a universal enveloping algebra, and this is a subalgebra that consists of operators that invariant under SO3. So it's give you a description of all SO3 invariant differential operators in R3. It can be done in any dimension, but I choose the first not trivial case, n equals 3. So when you have the algebra, the question about Casimir operator. So in SL2, in SL2 and in SL3, we have Casimir operator. So in SL3, it's very popular in physics, so-called orbital angular or simply angular momentum operator. It's sum of squares of these three rotations. And also there is Casimir operator in SL2. And the funny thing that it's the same operator M, but in terms of operators that we use to construct SL2, it has the following form. So this is the situation that we have in this algebra of delta is a diagonal vector field. X dx, y dx. So this is a really funny situation. So you have this algebra of differential operators with polynomial coefficients. inside of this SL2 and SL3, we have universal enveloping algebras, and especially this one important for us because it gives us all invariant SL3 invariant differential operators. But this is two universal envelope algebra. They have a non-trivial intersection. Namely, if you take take Casimir and degrees of Casimir, they will be an intersection. So this is very funny algebraic structure. And by the way, this algebraic structure allow us to avoid integration in consideration of spherical harmonics. I will show you. Okay, and also one observation. It's really related to geometry of unit sphere, and on the unit sphere you have Laplace operator. So if you take this operator M and restrict on, say, on the functions on the sphere, you can consider that you have, say, functions on the sphere, on the space, say, some homogeneous functions, and just apply M for them. It's the same that you will apply Laplace operator for restriction on the sphere. So, and
you take restriction on the sphere of what?
Functions. You take function, yes. Say homogeneous of degree k. Yes. Now you take this operator M and apply it to this function. It's result restrict on the sphere. You will get some function sphere. Now you take this, say, homogeneous of degree 0, for example. So take the restriction of this function on the sphere and take Laplace operator that lives on the sphere because you have standard metric there. And these two functions will be the same. So it's, I say that it's restriction. So Laplace on the sphere, it's a restriction of this Casimir on the sphere, but restriction in the sense that I said. It's not important for us, simply observation why. So it's really the question how to work in pure algebraic manner when you do something on the sphere. Okay, so first relation between homogeneous polynomial and harmonic polynomials is the following. So if you take, so pk is homogeneous polynomials of degree k. Delta, this is Laplace, so you have this arrow, and you have also a kernel of this is by definition our harmonic polynomials. So this part is obvious, and you can check it that it's also epimorphism. So we have this exact sequence. So if you compute this, you will get the dimension of the space HK is 2k plus 1. Oh, yeah, but k not important here. It's can be. It's not very much important. Okay, the second, it's also pure algebraic fact that polynomials, homogeneous polynomials of degree k, so this space pk, can be any homogeneous polynomial can be splitted or presented as a combination of harmonic polynomials of degree k minus 2i multiplied on this degree of distance.
Can you see the same R which you
it's, yeah, it's reduced, yeah.
Oh, can you repeat the last sentence? Because I don't understand.
We take polynomial, harmonic simply any polynomial, homogeneous polynomial of degree k.
Yes.
Now the claim that you can represent this polynomial as a sum of the following polynomials, harmonic polynomials of degree k minus 2i, and multiply on r squared in degree I. So, okay, this is, yeah, it's integer part, k divided by 2. So it's the second observation, and really it's okay. Just in few minutes, I will discuss it once more. This statement, it's really very easy to see if you consider another sequence, but I will do it later. So first of all, let's see what happens if we apply our Casimir operator M to homogeneous polynomials of degree k. So for M, we have two expressions. One is sum of rotations, square of rotations. The second is delta, small delta, and small delta. Small delta on this polynomial hk acting as a multiplication by k. So the capital delta is give us 0. So when you apply m to this, you will get simply the same polynomial multiplied on this one. So if you remember the statement that m is really, if you restrict on sphere, you will get Laplace operator on the sphere. So it simply says that if you take homogeneous harmonic polynomial of degree k and take restriction of this polynomial on sphere, then you will get eigenvalue, eigenfunction for Laplace operator, and this is eigenvalue. And this is, by the way, why it's this harmonic polynomial so important. They simply give us splitting of Laplace in some of these operators multiplications. This is what I just said, that restriction harmonic, spheric harmonics on the unit sphere give us this is eigenfunctions for Laplace. And this is can be there are two ways of proving that you will get really basis, say in L2 on sphere. It's approximation by polynomials really give you approximations by spheric harmonics.
Or dimension, or you can calculate dimensions, no?
Yeah, we did it. The dimension of HK is it's 2k plus 1.
Yes.
So we have dimensions, we have eigenvalues, everything we have in hands. Okay, so we will use this observation about this M, action of M on harmonic polynomials, just to construct some projections in homogeneous polynomials of degree k on the harmonic polynomials of degree k minus 2i in the following way. So what we know about M? So M, it's acting on harmonics just by multiplication of this minus k and minus k plus 1. It's also commuted with this multiplication by R. Really, M computes with all these operators that we use it to construct Casimir or construct elements from SL2. So R square there. So M compute also with multiplication by R. So it means that if you apply M to this is splitting of operate of polynomial in this form. So if you apply M to this, you will get simply it will be commuted with this one. So it will be M applied to this polynomial, but N applied to this polynomial give us the same polynomials with this multiplication. So really in this is splitting applications of M, it simply means that this is harmonic parts will be multiplied by corresponding eigenvalue. And this is give you immediately a way to construct projector, because projector should be something that it should be polynomial of M is the first one. And this polynomial we take in such a way that it will be on when in this product we will get. So if you take this lambda I, so this is eigen values of our M. So if you take and we want to take projection on the I component, it means that this polynomial should be equal 0 for all lambdas except lambda I. On the lambda I, it should be equal 1. So this is the formula for this polynomial. So it means that if I take this polynomial, I can construct components of the decomposition of our polynomial in sum of harmonics. Oops. Now the sequence that I promised to say, the following is exact. So it's more or less obvious because this is projection on the space, and the kernel of this projection, it's just by definition, it's higher or higher degrees polynomials. Low degree k minus 2 polynomials. So what we can say from this, it's, by the way, it's give you okay, I will skip it. But we will use this sequence to define product in harmonic polynomials. It sounds completely crazy. So you have harmonic polynomials. There is this polynomial that Laplace operator will send to 0. And now we want to multiply them. So yeah, it's not derivation, so it's very difficult to believe that if you take product of them, you'll get once more harmonic polynomial. But there is another way of doing. So we take two harmonic polynomials. Oops, this HK, HL. Take their product. It will be homogeneous polynomial of degree k plus L. And take harmonic part of this. So take this projection. So result will be harmonic polynomial. And so what we did, we constructed from two polynomials degree k and L, harmonic polynomials degree k plus L. And it's really, if you just look it on this exact sequence, it's really what its sequence says you, that if you take polynomials and divide it by a square multiplying polynomials, you will get this harmonic polynomials in this. And so multiplication is this factor, in this quotient, it's this exactly this. Okay, this is explicit formula for this projector when we take projector k0 or k plus L0. So this is, and what is important, it's once more this explicit formula, and it's involved only it's some polynomial of this is Casimir M. So this is a result of our observation. So if it takes spherical harmonics, we will get graded commutative algebra, NSSU certainly, with respect to this new product. And this algebra generated by linear functions. Linear functions, you know that they are harmonic. And relations that satisfy this functions is this one. So x squared plus y squared plus z squared equals 0. It's practically obvious from previous exact sequence. But what we can say is that harmonic polynomials, if you take complexification of this space, it's simply algebra of regular functions on the null form, on this one, in history. Okay. And so this is just a short example. If you take x multiplying x, multiplication, star multiplication, it will be x squared minus a squared divided by 3. If you take multiplication x and y, it's simply the standard multiplication x, y. Okay. So it's what I said, that this space harmonic spheric harmonics it's vector space of dimension 2k plus 1, and it's really irreducible representation of SS3. Now, so we have linear action of simple group SO3, and then Hilbert's theorem says that polynomial invariants of this section, they form some finite generated commutative algebra, polynomial invariants. Certainly, if you take rational, they give you field, but we just should ask Rosen. What? Yeah, polynomial algebraic invariance, right? And if you take now, I'm talking about algebraic invariants now. The second page will be just about differential. So Rosenlich's theorem is also applied for this situation, and what it says that if you consider rational algebraic invariants, then this field will have transcendentness equal codimension of regular orbit. I will back to notion of regular orbit very soon. So now what you can say about regular orbits of this section. So what can be easily checked that regular orbit, if you take harmonic polynomials of degree k, where k is 2 or more, then they have this codimension, and they have codimension 1 when k equal 1. So k equal 1 is simply action of SS3 on the three-dimensional space, and we have certain codimension 1 orbits. And so it means that to define regular orbits, we need 2k minus 2 algebraically independent rational invariants for k, bigger or equal to, and only one for dimension 1, for degree 1. Now about differential invariants, what you can say about them. So this is affine manifolds, and this is sequence says us that dimension of this affine manifolds is 2i plus 4, and I runs between 2 and k. So once more, regular orbits, and this is really, the notion of regularity every time that I will use. So regularity means that on this quotient, really, if you remove some singularities, it will be algebraic manifold, and then regular orbits, it's simply smooth points on these manifolds. And so after this, you can say that rational invariants of order I, so rational functions on this quotient, has this is degree of transcendence degree. Is it clear? Yeah, it's 2i plus 4 minus 3, it's 2i plus 1, yeah. So, so this is difference between transcendence degree of algebraic invariance and differential invariance. So it will be 2k minus 1 for algebraic case, and this is 2i plus 1 for level I. And if you take level k, so it will be 2k plus 1. So it's slightly bigger than algebraic one. And now, so how we use invariance, algebraic invariance? Algebraic invariance, if you take orbit and restrict algebraic invariant on the orbit, it will get number. And so to fix orbit, you simply should take a reasonable number of, if you talk about rational invariance, you should take this number of rational algebraic invariants in general position and take the values on the orbit, and you will get, you define your orbit completely. But what we will do with differential invariance. So let's take a regular harmonic. So this regular point in this is a space HK. And then you can check it that if you take SO3 orbit of 2Z, so 2Z of H, it will be just three-dimensional submanifold in 2Zs. And now apply group SO3, you will get six-dimensional submanifold in 2Zs. So in this is equation E2.
So you move not a point, you move the whole.
The whole, yeah. So G2H is this three-dimensional manifold constructed from second jets of our H, and we move it along SO3, so we'll get six-dimensional, and this manifold E2, it has dimension 8, and so to define this orbit, we need only two invariants, two differential invariants of order 2, and it doesn't depend on K. So it means that to describe orbits of regular harmonics, we need only two relations between invariants of order 2. So it's you see that it's much more rational than use all algebraic invariants. Okay. Now let's go to computation of this differential invariance and after see what we can say about algebraic invariance. So first I will construct invariant Coq frame. So we have this is obvious invariant, so R square, and this is 0. It should be U 0, 0, 0. I will simply write U so in jet notations. So if you take total differential, so certainly from this it's simple differential. We give two differential one forms. So the first one is the differential of this, and the second one is the differential of this. Yeah, because this G minus 1 and G0 they invariant, so we'll get invariant three invariant two forms, and one more. So we take the cross product. So you see, because we have the metric here, it doesn't matter what we use, differential forms or differential or vector fields. So if you just think that it's different vector fields, take the cross product as we learned in vector analysis, I think. So, and you will get this is the third form. So these three forms, they are SO3 invariant, and they give us invariant coframe. By duality, we can get invariant frame. It's three total derivations. So this is the first one. It's with the analog of this diagonal form, diagonal vector field. So this is two derivations, and this is the third one is the derivations that you'll get from cross product. So this also SO3 invariant, guys, and it means that if you take invariant, apply any of these derivations, you will get once more invariant. Okay, so let's see what we can get on the first step. So we have this is two invariants. If you apply this is D2 to this is G0, you will get this invariant, and this is also obvious invariant. It's just square over gradient, and apply to G1 once more, you will get this invariant. But now this is invariant of second order. This zero order, this minus one order. This is second. This is the first order, and this is the second order invariant. Okay. Now let's use the trick. Group SO3 action of group SO3 on R3. It's affine action, so it means that it preserves affine connection of R3. So using this affine connection, I can split jets in sum of symmetric degrees of R3. So, and if I take i's components of the splitting, I will get this as differential forms of degree I, these ones. And because they just, the splitting we constructed by using this affine trivial affine connection, so they invariant of a group of affine transformations. Now, if I take the, I will remember that I have metrics, so instead of these forms, I can get differential operators. So this is differential operators, but they will be SO3 invariants because I use it SO3 duality here.
But
Oh,
this T is total.
Here
Yes.
is it total. Yeah.
Total.
Yeah, this is total. It's simply differential, but this is total. Yeah. So it means that it's not invariant in the sense that we have invariant functions. It's invariant in this, in this case, it's invariant tensors or differential forms, and here this invariant differential operators of the of the I. So together with invariant frame, we have also this infinite number of invariant differential operators. Okay, now let's do the first observation. So we take this our coframe omega 1, omega 2, omega 3, and the standard coframe dx dy dz we can just represent or express in terms of omegas. So if you take this expression and put it in expression for theta I, so instead of dx, you will get the expression in omegas. You will get the representation of this theta I as a sum degrees of these omegas with some coefficients. But now just look at here. Yeah.
You take this theta and you
Yeah, it's I use this dx, this coframe dx dy dz. Yeah, yeah, and now just to take this expression, put it in this one, and I will get something like this. But in this form, this is invariant, but this is not invariant, and this is not invariant. Now we have this is invariant, and this is also invariant. So this is T, I1, I2, I3, they invariant. Invariant, and you can see easily because when you will solve these equations, they will be rational functions. Really. And so this is a rational functions. And so it means that we will get this number of rational functions T, I1, I2, I3 instead of this coordinates, jet coordinates U, G, E1, E2, E3. So it simply means that if you take, by definition, what is a invariant differential, it's invariant differential, differential invariant, it's some function that depends on these coordinates. But if you will write a simply function in this coordinate, certainly you will get this probability 100%, you will get non-invariant. But now it's because I use it instead of this U, I1, I2, I3, I use another these functions. Certainly, if I take any function in U's, I can express the functions in T's. And opposite. But if I looking for invariance, then I will do something like this. So I can simply take rational functions of these T's. And for reasons that you can express U's and T's, it simply means that all rational invariants will be rational functions of these T's. Okay. So just a simple example. First of all, just look at on this as operators. So they invariant, and if you take this is operators, the invariant operator. So if you apply this operator to invariant, you will get invariant. So now let's apply to our first non-trivial invariant, namely function u. Then you will this sum, but these guys will be in squares. So and this is says us that if you take this one, you will get some invariant. Just look it on this one. It depends only on this is ui's only highest degree I. So it's really algebraic invariant because when we apply to differential to homogeneous polynomial of degree I, you will get simply number. And what is a fun observation that this is give you just not length, but square of length of this of this form. So this is just a short example what happens in small order. So if for the 1, you will get this invariant derivation, you know about this. If for the 2, we have this second order operator. So if you apply this to u, you will get this square of gradient. And this what says here, it's exactly what was there. And if you take, oops, sorry, it should be theta 2. So you will get this invariant. And you see this is really, it's invariance of second order, it's easy to understand because if you take second jet and take only highest derivatives, it's the same as quadratic form on harmonic quadratic form on the three-dimensional space. What means harmonicity? If you take Hessian of this form, then conditions that is harmonic is simply the trace equals 0. So harmonic polynomials of degree 2, you can identify with the matrices, symmetric matrices 3 by 3 with zero trace. And this guys is simply square trace of square of this matrix. It's how we define really distance on matrices. Okay. Now the statement. So you see that really, if you just look it on this sequence, you see that on each new step. So if you know say invariance, say differential invariance, say or for the 3, then to find invariance for the 2, you should add simply 2 new independent invariants. So how to get it? So what we do, we'll take invariance simply here and take 2 invariants here. Say, for example, this one we had before 1 G to 1, two invariants of second order, and take apply this derivation nabla to this, and you will get 2 invariants here. Now take this 2 invariants here. Once more apply this nabla, you will get 2 invariant A, and so on. So really, generation of invariants, you can start say from this level, and simply after applying this nabla, you will get all generators and differential invariants. Yeah, yeah, it's correct. Simply K, I stop it here just to stress it, but it's really you can compute it for as long as you want. Simply, if you will restrict on polynomials, say of degree k, then everything that concerns to k plus first and second derivatives, they will just vanish. Okay. one observation more. So this is simply trivial observation, but it's fun observation and very useful. It's the following. It's what we know, that if you take function on jets, then you can consider this function as a nonlinear differential operator of order k. Just applying two functions, you should take your function phi, this and restrict on section of kjet of function f. Now, what means that you have invariant? So if this phi is invariant, so what means? It means that this nonlinear differential operator for the k will be SL3 invariant. So in some sense, what we did when we described all SL3 invariant, then we simply found all nonlinear differential operators of, say, order k that invariant under SL3. And so it gives us a monoid structure on the field of rational say invariants. The identity in this monoid, it's obviously this is invariant U, because it's give us identity map. And so, and this is я не просил. Так, and so now I just will, I practically finish, but I will simply sketch some also observations. So how to get algebraic invariance from differential invariance. So it's, you can see that it's easily to get differential operators like we just see. Just take the trivial invariance in, say, in order 2 and apply this number, and you will get really all invariants. And take certainly some function of them, and you get all invariants. It's not so easy to find, say, all invariants in some degree k. It's 2k plus 1 vector space. There is some action there, and to find invariance, it will be not the easy task. So when k is equal to and 1, it can be, I think we know this from linear algebra, but say in k equals 3, it will be a problem. And so what we can do? First, let's introduce the notion of weight. So for this, we take the following vector field. It's on G0. And so W star, this is prolongation. I don't care about, so it will be infinite prolongation because I don't want to specify how many times we should prolong this. So now I will talk about polynomial differential invariance, but we know that if you take rational differential invariant, it does matter. So you take numerator and denominator of this invariant, you will get two polynomials. So if you take polynomial, then the weight, it simply say us what happens if you apply this vector field to this polynomial. Prolongation of this vector field to this polynomial. If it will be multiplied by this v of I, so we say that v of I is this weight of this polynomial. Okay, how to reformulate this property? It says that if you take, say, homogeneous polynomials of degree k, and compute value of your invariant I on this polynomial h, then this will be also polynomial, but degree, this is WI. So it means that application of this computations of value of your invariant on homogeneous polynomials of degree k give you polynomials of degree WI. And now how to construct algebraic invariance from differential invariance. So take differential invariance of, I will say simply weight W, and take polynomial h, harmonic polynomial of degree k. Now let's take value of our invariant I on this polynomial. You will get a homogeneous polynomial of degree W. Take this polynomial and take harmonic part of this polynomial. So it's polynomial degree double V. So we have really a chain of harmonic parts of this polynomial. So this is what I take 2L part of this polynomial, or double V minus 2L part of this polynomial. Then I will get harmonic polynomial. And now I simply take weight or length of this harmonic polynomial.
What is G?
G, this is operator that we use it in invariance that corresponds to length. These ones. So they simply computed the lengths of these polynomials. So when you will take this one, you will get simply a scalar, just some number. It means that this invariant is just composition of these three invariants with composition in monoid structure of our invariants. So this is simply will be algebraic invariant. And as we saw, so this is just obviously differential construction, and the main part, this guy also differential construction. It involves this Casimir operator, but it's polynomial of Casimir operator, but it's differential. So everything differential here. Okay.
And all algebraic invariants are obtained in this way.
All algebraic invariants automatically are differential invariants. So just because when you write,
Yes,
it's obvious. So the question is, I have enhanced some differential invariants, and it's very easy to get them. So now the question, how to construct algebraic invariants from this differential invariants? And this is just given by a composition of these operators. Okay. Thank you for your patience.
Okay. I don't know whether you can hear me. Thanks a lot. Any questions, remarks?
Just may I ask you, can you repeat please about how the whole duality?
No, it's not duality, it's pair. It's called whole pair. It means that you have this usually commuted, like in this Lie algebra, two commuted Lie algebras, and with common Casimir. And if you can say, if you say, look in say represent want to describe say reducible representations or invariants of some of the algebra. So we're trying to find like we did here. So we have this SO3 and we want to find invariance of this. But we constructed this SL2, and this is give us the way first to construct this space HK, harmonic spaces, reducible representations, and also to find invariance. So this is just very very beautiful picture. Two mutually commuted Lie algebra with common
Okay, more questions? Remarks? Well, either no question or you cannot hear me. The two options. I hope you do hear me. Okay, then thank you very much. We skip the next session by some personal reasons, and we meet in 2 weeks with the talk by Rafael Vitala. So goodbye. Thank you for participating.
Bye.
Thank you. Goodbye.
До встречи.